Hi guys, this is John Hashmat and welcome to Physics Simply. We discussed before voltage, current, and parallel and series connections in a previous video. In this video, we will be talking about resistance and how it affects current and potential difference or voltage in a circuit. In front of you, we have a power supply connecting positive and negative terminals. We have it connected to a conductor. That's an alloy of silver and copper. We hooked up a voltmeter to see the potential difference across the conductor and an ammeter in series to see how the current changes. Now, I'll be using a 20 centimeter wire of copper and silver alloy, and its diameter is about 0.40 millimeters. I'll only be using 0.1 volts so that the wire does not get too hot while we're doing the experiment. So now we're going to switch on the current. So that's 0.1 volts. I'm going to adjust it a little. 0.1 volts. That's giving us a current of 0.24 amperes. Now, to calculate the resistance, we need to divide the potential difference by the current, which would give us about 0.42 ohms. That's the unit of resistance. Now I'm going to adjust the position of the terminals of the voltmeter so we can measure the potential difference across 10 centimeters of the same wire. So we'll still have 0.4 millimeters diameter and the same alloy and same material, only we'll be measuring the energy across half the wire. So it's taking about half of the previous voltage, so that would be 0.05 volts. And the current is still 0.24. Now, if we want to calculate the resistance, we will find that it will be about 0.21 ohms, which is half the previous value. That means that half the wire has half the resistance. So the length of a wire or a conductor is directly proportional to its resistance, or the resistance is directly proportional to the length of the wire. Now, let's try to measure the same thing, but with a 0.19 millimeter diameter. Now you can see I have moved the connections from the upper wire, which had an 0.40 millimeter diameter, to the lower wire, which has a diameter of 0.19 millimeters. And now we're going to use 0.1 volts again. And now we can read the current here is less than 0.1, it's about half, so it's 0.05 amperes. Also here, to calculate the resistance, we divide 0.1 by 0.05, and we get a resistance of 2 ohms. Now you can notice here that when the diameter was decreased, the resistance increased. You can also see that during this transition, the diameter was almost multiplied by half, so the area is multiplied by a quarter. That made the resistance to be multiplied by 4. This means that the resistance is inversely proportional to the cross-sectional area of a conductor. So now resistance is directly proportional to the length, but inversely proportional to cross-sectional area. Now we're going to use a wire of the same diameter as this one, but made of copper and has the same length. Now I've connected a copper wire which has a length of 20 centimeters and the same diameter, which is 0.19 millimeters, to the same potential difference as before. So I'll be using 0.1 volts. As you see, the pointer here is reading a very high current. So I'll be changing the scale. Now I've adjusted the scale on the ammeter, so we'll be reading from the top numbers here. Now I switch on the current, adjust the voltage to 0.1 volts on the voltmeter. Now the reading here is about 2 amperes. So I have a current here of 2 amperes. Now to calculate the resistance, we divide 0.1 divided 2. That gives us a resistance of 0.05 ohms. You see here, these two wires had the same dimensions. They have the same length, same diameter, same cross-section area, but they still have the same, different resistance. That's because they have different materials. So another factor affects the resistance here, which is the material. We call the property that is consistent with the material resistivity, and we give it the symbol rho. The higher the resistivity, the higher the resistance. Since copper had a lower resistance than this alloy, that means that it has a lower resistivity. So now, to sum it up, resistance is directly proportional to length, directly proportional to resistivity, but inversely proportional to cross-sectional area. That leads us to an equation that the resistance can be calculated as resistivity by length over cross-sectional area. Now, if you like this video, please like and subscribe to the channel so you don't miss any more videos on electricity and physics in general. Thank you, and see you in the next video.